On screen, there is a similarity matrix and nodes A to H. These nodes can be the images are slices from one 3D volume, but the stack is shuffled. In the true order, A is first and H is last. Our job is to recover only the order. What do we usually do for this problem? It's called fully pairwise similarity ordering. Start with node A, compare it to every other node, and write those similarity scores into the matrix. Then repeat that for all nodes until you've filled it out. Because the slicing process is monotonic, the similarity between two images goes up roughly linearly as their true distance gets smaller. So in theory, the matrix should look strongly diagonal. Each node's top scores are its true neighbors, and the left-right neighbors' scores should be about the same. From that pattern, you can recover the correct order pretty easily. In practice, there are two big issues. First, doing the expensive comparison for every pair is wasteful. We'd like to find true neighbors without touching all pairs. Second, real data is messy. Noise and artifacts blur the diagonal. So we also need a way to read the order that's robust to imperfect scores. Here's the plan to solve problem 1, computational cost. To cut comparisons, we mix graph ideas with randomness, a process we call graph condensation densification. The goal is a sparse graph with enough links to sort correctly. Step 1 is a Borufka-style phase with a fixed similarity threshold. For each node, we try a small random set of other nodes. We keep a link only if its score is above the threshold. Low-score pairs are ignored. They're likely far apart in the true order. We keep adding qualifying links and merging components until all nodes are in one connected component. Along the way, we've built a simple spanning tree. This costs roughly O of n log n and gives a backbone that's good locally, but may be wrong globally. For example, A and B can still end up far apart in this temporary graph. Next, we add shortcuts. We find two nodes that are farthest apart in the current graph. From one of them, we compare to all nodes and add every link above the threshold. Those shortcuts pull truly adjacent slices together in the graph. We repeat this 2 to 3 times. Then we do a simple double sweep BFS through the improved graph to get a working left-to-right backbone. Now we make the information along that backbone more dense. For each node, within a small fixed window K, we try the remaining pairs and keep any above the threshold. This cheaply fills in missing local links we'll need to settle ties. Overall work is about O of n log n plus k times n, with k the window size. We end up with a very sparse but informative link graph that stands in for the full matrix. To fix the issues that come from unclean data, we use a greedy algorithm based on a few chain rules. It lets us recover the correct 1D order from a sparse matrix. We call the final result the superchain. First, we build a tree graph from the current sparse matrix, and we map similarity to the line style. Thicker edge means higher similarity, and closer in the final order. Next, we go through all nodes again, and for each node, we keep only its strongest pair. Each node makes this choice independently. If a node was already picked by someone else as their best pair, that doesn't stop it from linking to its own strongest partner. After this pass, the messy image stack naturally breaks into many mini-chains. Then we try to merge those mini-chains by adding each node's second best link. But before merging, we declare 3 chain rules. Maximum chain rule. If multiple nodes try to link to the same node, we keep the strongest one. Unbroken chain rule. Once a chain forms, you don't break it in the middle. Chains can only merge through their 2 endpoints, and you can't link the 2 endpoints of the same chain. Fallback chain rule. If the matrix has no info about the current endpoints of the remaining mini-chains, we fall back one step inward to find a match. If that match works, we merge the 2 chains at the endpoints closest to that fallback point. So in our example, because of the maximum chain rule, even though C is the second best for both A and B, the merge between chain A to B and chain C to D happens at B to C. Also, because of the unbroken chain rule, the E to G link is automatically dropped. Finally, to merge the last 2 chains, the matrix has no direct info for the 4 endpoints, so we use the fallback chain rule to look for related entries. Once we find them, we try to link, but due to the unbroken chain rule, C and F can't link directly. We have to merge via D to E, which are the closest endpoints, and that gives us the final ordering.